In this video, we are going to discuss about single-tuned amplifier. This single-tuned amplifier, it uses one parallel tank circuit as a load in each stage, and all these tuned circuit in the different stage are tuned to the same frequency. So you can see, let me draw the circuit diagram. So this is your tuned circuit. This is connected to a common emitter transistor, and RE and R1 R2 is your biasing resistor, and we know that we are using a self bias for the biasing, and CC1 and CC2 is your coupling capacitor. So this coupling capacitor will block the DC signal and it will pass only the AC signal. So this one is connected to the next stage of the single tuned amplifier, the circuit, and each of this tuned circuit are tuned to the same frequency. So this single tuned amplifiers are classified into two types. One is capacitively coupled and another one is transformer coupled or inductive coupled. Okay, so let me draw the equivalent circuit for this single tuned amplifier. So first we have a Vs source and it is connected to RC. So here I have drawing this equivalent circuit based on the hybrid pi model. So this transistor I am replacing by RBB followed by RBE. Okay, so the voltage across this one is VBE. Okay, so this is your base terminal and this is your emitter. Okay, so this is connected to a base to collector. Okay, and here you have a capacitor CBC. Okay, and GMVBE. GMVB is your gain followed by GCE. Okay, since this is a collector to emitter, this is your collector terminal and this is your emitter terminal, so this is GCE followed by the tank circuit. Okay, this is your L. For inductance you have a resistance, that is R, followed by a capacitor C, and it is connected to a to the next stage of the input resistance. Okay, this is for connected to the next stage of the RA is the input resistance of the next stage of the single tuned amplifier. Okay, so this is your R0. So we need to apply the Miller theorem. Okay, Miller theorem. So in order to remove this capacitance, so at the input side the CBC will become like this. Okay, so this is Vs followed by Rs, RBB, then RPE. Okay, So this this capacitor becomes CB. Sorry, you have here also you have one capacitor. This CBE. Okay. CBE, and this is CBC into 1 minus A. Okay. So this capacitance is replaced at the input side like this, and since it is forming a feedback from output to the input, it is forming a feedback. There is a connection. So in order to remove that feedback, we are using a Miller equivalent circuit. Okay. So at the output side, it is termed like this: CBC A minus 1 divided by A. Okay. So rest you are having this circuit. Okay. So since these two capacitors are in connected parallelly, you know the formula, right? So Ci I can write it as CBE plus CBC 1 minus A. Likewise, here I can write it as C equivalent. This two I can write it as C plus CBC A minus 1 divided by A. So again I am redrawing this circuit. Okay. So this is your emitter and this is your capacitor. The capacitor I am replacing it as C equivalent. Okay. I think I have forgot it to. Okay. See this GC, this GCE I can write it as 1 divided by RC, right? That is equal to H naught E minus GM into HRE. So this I can approximate to H naught E. Okay, which is nothing but 1 divided by R naught. Now what I am doing is this inductor and capacitor, inductor and resistance, I am going to equate that one to LP in parallel with RP. Okay. So I am going to replace this term to this one. So we know that the addition of this one is we know that R is equal to Z is equal to R plus J omega L. So from this I can write Y is equal to 1 by Z, that is nothing but R plus J omega L. So I am going to multiply the both term by R minus J omega L. So if I multiply the both term, I will get Y is equal to R minus J omega L divided by R square plus omega square L square. This I can term it as R divided by R square plus omega square L square minus J omega L divided by R square plus omega square L square. Now I am going to multiply the both term by omega and omega. So this I can write it as 1 divided by Rp. If I multiply both term by J, okay, J omega and J omega, I will get plus omega square L divided by J omega R square plus omega square L square. This I can write it as 1 divided by Rp plus 1 divided by J omega Lp. Okay, so what is now my Rp? Rp is nothing but R square plus omega square L square by R, this one, right? So this I can write it as R plus omega square L square by R. So we know that since Q of the coil, okay, so Q of the coil is usually large, okay, so that omega L value is always greater than R in a frequency range of operation. So therefore I can write this one as omega square L square by R, okay, Rp, okay. In the similar way, I can write what is Lp. What is Lp? Lp is equal to R square by omega square L square divided by omega square L. This one, okay, from this equation. So I can write R square plus omega square L plus L. Okay. So since this is in the denominator, this get cancelled out. So I can equate L. P is equal to L. Okay. So we know that Q effective value is equal to QR value. Q is equal to omega R L divided by R. So you substitute in this equation. Okay. So we know that Rp is equal to omega square L square by R. So in this you multiply omega R by omega R. Sorry. So I can write omega into omega L So this I can write it as omega into omega L by R, right? So Q omega L divided by R, I can write it as omega Q L. Okay. So therefore I can write Q. Okay. Q is equal to Rp omega R L, Lp, because the Lp and the L value are same. Okay. So this Q effective is in other words I can write it as omega R C equivalent RT. Okay, I can write it like this also. So now what I am going to do is at the output side. Now so you can see at the input side. I can apply the Kirchhoff's voltage law. I can voltage divider rule. VB is equal to Vs into RBE plus RBE. Sorry, it is not Vs. from here. Okay, this is your Vi. So I can write Vi into RBE plus RBB. Okay. So now I can redraw the equivalent circuit. This is your R0 and this is your L and C. I am going to replace it like this, and you have a C equivalent and you have a input resistance of the next stage. Okay, now this is your at the output stage. Okay, so this I can redraw it as GMVBE. Okay, LP C equivalent followed by RT. So what is RT now? RT is equal to R0 in parallel with RP in parallel with RA. Okay. So what is the voltage, output voltage across this one? So this is nothing but V0 is equal to minus GM, since the current is flowing the opposite direction, GM VBE RT. Okay, so from this equation I can write what is VBE RBB plus RBE into RT. So my V0 by Vi, that is nothing but AV, that is equal to minus GM RBE dash divided by RBE dash plus RBB into Z. Since this whole value, right, that is your Z. So we need to find the value of Z. So what is Z? Z is nothing but RT plus J omega LP minus J divided by omega C equivalent. So this I can write it as R plus J omega LP, multiplying the both term by J and J, I will get 1 plus J omega C equivalent. This is your Z. So what is Y now? Y is nothing but R plus J omega LP plus J omega C equivalent. Okay, so this is not R, this is RT, right? So now you take RT common. If you take RT common, you will get 1 divided by RT plus J omega LP plus J omega RT C equivalent. So you multiply both term by omega R. Okay, 1 plus RT omega R divided by omega R J omega LP plus J omega RT C equivalent omega R by omega R. Okay, so we know that what is del? Del is nothing but a fractional change in the resonant frequency. So I can write del is equal to omega minus omega r, omega minus omega r divided by omega r. Okay, so this I can write it as omega by omega r minus 1. So 1 plus del is nothing but omega by omega r. So now you substitute this one, 1 divided by RT, 1 plus what is omega r LP divided by T, that is nothing but Q. Okay, so Q omega r divided by J omega plus J omega Q divided by omega r. Okay, so now you can take this Q common. If we take Q common and if we multiply J and J and whole term, I will get omega r divided by omega plus omega divided by omega r. So this I can write it as 1 plus Q. Okay, I can take J common. So what is minus omega r divided by that is 1 plus del plus omega by omega r is 1 plus del. Okay, so I can write y is equal to 1 divided by RT plus 1 plus JQ one plus del minus 1 minus 1 plus del. Okay, so this I can write it as 1 plus del the whole square minus 1 divided by 1 plus del. So 1 divided by RT, 1 plus JQ. So this I can write it as 1 plus 2 del plus del square minus 1 divided by 1 plus del. So here 1 get cancelled out. So 1 divided by RT plus 1 plus JQ. You take 2 del common. If I take 2 del common, del square divided by 2 del divided by 1 plus del. So here del get cancelled out. So the del value is 0 at resonance frequency. Okay, it's less than resonance frequency, and it is always less than 1. So therefore I can rewrite this one as 1 divided by RT 1 plus JQ2 del. Okay, this is your y. So therefore Z is equal to RT divided by 1 plus J2 del Q. So now you substitute this formula in this equation. Okay, third equation. So I'll get what is AV? AV is equal to minus GM RBE divided by RBE plus RBB into RT plus 1 plus J2 del Q. So this AV at resonance is equal to minus GM RBE divided by RBE plus RBB. So at resonance del value is 0, so you will get RT. Okay, so this is your fourth equation and this is your fifth equation. So now you divide 4 by 5. Okay, so AV by AV at resonance is equal to So this term get cancelled out, so you will get RT by 1 plus J2Q del by RT. So this is what you get. So here RT and RT get cancelled out, therefore you will get 1 divided by 1 plus J2Q del. So if I take the modulus, one divided by root of 1 plus 2Q del the whole square. So this value is nothing but 1 by 2. So I can equate this 2Q del the whole square is equal to 2. So I can write 2 del Q is equal to 1. So what is my del value? Del value is nothing but 1 divided by 2Q. So we know that what is del? Del is nothing but omega minus omega r divided by omega r. So what is del omega? Del omega is equal to omega 2 minus omega 1. It's a difference frequency. It is nothing but difference between the highest and the lowest frequency. Here I can write it like this, right? Plus or minus. So I can write it like this also. So here I am going to multiply omega r and omega r on both sides. Okay. So what is this one? Omega 2 minus omega r by omega r is nothing but del, and omega r minus omega r divided by omega r is another del. Okay. So I can write 2 del omega r. So what is my del omega? Del I can write this as del f, 2 del omega r. So from this I can write what is my del? Del is equal to del f divided by 2 fr. So you substitute here, del f divided by 2 fr is equal to 1 divided by 2q. So this I can write it as del f divided by fr is equal to 1 divided by q. Okay. So del f is equal to fr by q. So what is del f? Del f is nothing but a bandwidth. Difference in the frequency is bandwidth. So we know that what is the value of q? Q is nothing but omega r RT C equivalent, right? So if I substitute this one, my bandwidth is equal to fr divided by 2 pi fr RT C equivalent. This is nothing but 1 divided by 2 pi RT C equivalent. Okay, this is your bandwidth for the single tune amplifier, and this is your gain for the single tuned amplifier. So I hope this video is useful for you. Thank you very much.